So now we will go back a little bit more to our modular approach to deep learning, and we will define one module ourselves. And what does it mean to define one module in terms of programming? So the first thing to do is to define the parameters of this module. So here I want to implement the dense module that we have seen before. It's a linear transformation. Here we'll have a matrix W that will, so my module will take it as an input. I will take the matrix multiplication W8 plus this bias B. So it will be the transformation. It will be how I take a data as an input and how I transform it as an output. At the beginning, we don't know which values W will be. So we will initialize this module to random values, and we will let the model to learn the values in W and B. W and B are my parameters. So okay, I define how the information will be transformed in one direction. So we'll take this simple example where I'm constructing a very simple computational graph. Here I represent these images as this tiny vector, 4-dimension vector. It's only for the exercise. This vector will be processed by a dense module. I will obtain another representation of a different length. This representation will be processed by an activation function here. I've chosen a ReLU. So I obtain a new representation. This one will be given to a dense, which will bring this representation to the right output. So here I just want to detect is it a 2 or not. So I only want one scalar at the output, and the dense can do it. Since I want to predict the probability of 2, I will use the sigmoid function here. I will have my probability. I will give it to a module called the loss function. And here, it's different from the performance metric. The performance metric must be used for any kind of algorithm, any kind of models. Here we are using a loss function that will be differentiable. And not all performance metrics are differentiable. So we are using a surrogate. If your performance metric is differentiable, use it. It's really the right thing to do because you will be optimizing the real metric. If your performance metric is not differentiable, keep your performance metric and try to find a surrogate that will estimate it well, that will approximate it well, but that will be differentiable. And this module, this loss module, will take 2 inputs, the prediction of my model after the sigmoid, and the real target. And it will give me one loss value for this specific example. So now I'm interested to change the values of my parameters. Now we just have default parameters. Maybe I initialize it with uniform distribution. It's only random variables. The model will not work well. It's just random transformation. I want to change the parameters of my model so that I minimize the loss. And we will use this concept of derivative so that I will try to compute if I change one parameter, is my loss increasing or decreasing? And with this information, I will change little bit by little bit all my parameters to minimize the loss on the training set. Is the change on this parameter, if I increase it, will it have a positive or negative impact on this training example? This is the question we want to answer. So here, one thing we can do is to not use backpropagation. Backpropagation and computing the derivative seems too complex. We just implemented how an input will be transformed as an output, and we think that it's enough to compute the change of these parameters on the output. And there is a way to do it. What I will do is that I will take my loss function for this example with the current parameters of all my network. I will choose this parameter here. I will increase it by 10 to the power of minus 6, just to see a little bit, if I move this parameter a little bit, how my loss will change. And I will divide it by the size of the modification on this parameter. And it will give me, if I change by epsilon I, is my loss will increase or decrease. It's a valid algorithm. And in fact, it's really a finite difference method. For you who are familiar with computing this kind of thing in physics, if you want to do it properly, you should probably use this formula. It's the loss for the parameters minus epsilon I, and we compare it to the same parameters, but with this one plus epsilon I, and we divide it by 2 epsilon I. And it's a finite difference method to approximate the derivative, the partial derivative of the loss with respect to epsilon I. When I was programming backpropagation, I was using the finite difference method to test my implementation. If I take epsilon I to be very small, like something like 10 to the power minus 6, the output of the backpropagation algorithm should be very close to this one, or the other way around, because this one is an approximation. Okay, so what is the complexity of this finite difference method? So if I have n parameters, I need for finite difference, I need 2 forward. I need 1 forward where I will take the image, I will change the parameters here, I will take the image, I will propagate forward, retrieve the loss, then I will do the same thing but by increasing by epsilon I instead of removing epsilon I. So there is 2 forward in my model, and I must do it for each parameter. And as I said, in deep learning, we have hundreds of millions of parameters in the most complex model. So it's 2 times millions of propagation to just have the information, if I change any of the parameters, how the loss will change. And I didn't update any parameters yet. So it's super slow to use finite difference method to see the impact of a parameter. So instead, we will use backpropagation. With backpropagation, as you will see, it's only 1 forward and 1 backward for this example. The complexity in terms of forward pass does not depend on the number of parameters. 2 graph traversal instead of millions of graph traversal. That's why backpropagation is so important.